there are plenty of limits that are really quite hard to evaluate. Here's an example. Take the limit as x approaches 4 of the square root of x minus 2 divided by x minus 4. Admittedly, that limit's not really that difficult to calculate, right? The limit is 1/4. But we can also think about this maybe a little bit more intuitively. Look at what's going on. The limit of the numerator is 0, right? As x approaches 4, the square root of a number close to 4 minus 2 is close to 0. And the limit of the denominator is also 0. And because the limit of the denominator is 0, I can't just use my limit of the quotients as the quotient of limits deal to evaluate this limit, right? I'm genuinely in a difficult situation. And the problem is that the numerator, being close to 0, is trying to make this ratio small. But when the denominator is close to 0, it's trying to make this ratio really big. And neither the numerator nor the denominator win the game, right? Those two forces balance off, giving the answer of 1/4. But why? Well, we can see this geometrically. So here I've graphed in green the function square root of x minus 2, that's the numerator, and in orange I've graphed x minus 4, y equals x minus 4. And you can see that when x is equal to 4, these curves cross the x-axis, because when I plug in 4 here I get 0, when I plug in 4 here I get 0. But also note that the green curve is getting closer to 0 more quickly than the orange curve. Let's replace those two functions with the approximations that we get by using the derivative. Now, let me replace this green curve with the tangent line to the green curve at the point where the green curve crosses the x-axis. Well, here I go. Here's a picture just of that tangent line. Now, I could compute that tangent line by doing a little bit of calculus. Right, this function is the square root of x minus 2. If I differentiate that, I get 1 over 2 square roots of x. That's the derivative of the square root function. And the derivative of minus 2 is just 0. Now I can evaluate that derivative at 4, and I get the derivative is 1/4. And that's the slope of the tangent line here to the green curve. Now I know that my tangent line should cross through the point 4, 0. So here's the equation of the tangent line in point slope form, and I can rewrite this a little bit more nicely as y equals 1/4 x minus 1. So what happens to the limit problem when we replace those expressions by their tangent lines? So instead of thinking about this geometrically, I can just look back at this original limit problem and replace these pieces by their tangent lines. And we calculated the tangent line to the graph of the square root of x minus 2 to be 1/4 times x minus 4, and the denominator is already a straight line. So if I replace the numerator and denominator by these straight line approximations that are good for inputs near 4, this original limit problem is transformed into this limit problem. But this limit problem is really easy to do, right? I've got an x minus 4 in the numerator and an x minus 4 in the denominator, so this limit is 1/4. It's important to emphasize that we really haven't done anything new here. We could have calculated this limit even without thinking about derivatives and tangent lines. But this perspective opens up a new way of approaching some limit problems. So here's how I can package this up into a situation that's maybe useful more generally. Suppose I got two functions. I got a function f and a function g. And let's suppose the limit of f as x approaches a is 0, and the limit of g of x as x approaches a is also 0. And just for kicks, let's suppose that f and g are also differentiable, twice differentiable. I want these to be really nice functions. Now let's suppose I want to try to calculate the limit of f of x over g of x as x approaches a. This might be a difficult limit to calculate. But what we just saw is that we could try to understand this a little bit better by replacing f and g by their tangent line approximations. Another way to say that is I'm just going to replace f of x and g of x by their approximations that I get from considering their derivative, right? So the limit of f of x over g of x should be close to this, because f of x is close to this, right? It's the value of f at a plus the derivative of f at a times how much the input changes when I go from a to x. That's approximately f of x. And this denominator should be about g of x. It's g of a plus the derivative of g at a times x minus a. That's about g of x. So if you believe that the numerator and denominator here are approximately f of x and g of x, you might then believe that these limits are also equal. But this is a really great situation to be in, because f of a, say, is equal to 0 if f is continuous there, maybe since it's differentiable, and g of a is also equal to 0 since g is continuous. So that these f of a and g of a terms go away. And then I've got an x minus a and an x minus a term there, so those also cancel, and all I'm left with is just f prime of a divided by g prime of a. So it seems like if you're trying to calculate the limit of this ratio, what's really relevant is understanding something about the derivatives of your numerator and denominator separately at that point A. The precise statement of this is usually called L'Hopital's. So here's a statement of L'Hopital's rule. Suppose I got two functions f and g, and they're differentiable for inputs near A, and the limit of f of x and the limit of g of x as x approaches A are both 0. So these functions' output is very small when their input is close to A. And the limit of the derivative of f divided by the derivative of g as x approaches A just exists. And the derivative of g is not 0 when I evaluate that derivative for inputs near A. If all of these conditions are true, then I get the fantastic conclusion that the limit of f of x over g of x is the limit of the derivative of f over the derivative of g. And the hope is that this limit is easier to compute than this original limit. Let's try to use L'Hopital's rule in a much trickier context. So here's an example. Let's compute the limit as x approaches 0 of cosine x minus 1 plus x squared over 2 all over x to the 4th. Now, the limit of the numerator is 0 and the limit of the denominator is 0. So this is the sort of situation where we could apply L'Hopital. So let's do it. What does L'Hopital tell us? Well, L'Hopital tells us to consider the derivative of the numerator divided by the derivative of the denominator. The derivative of the numerator is, well, it's a derivative of difference in a sum, so it's the derivative of each of these terms. What's the derivative of cosine x? That's minus sine x. The derivative of minus 1 is 0. And the derivative of x squared over 2 is just x. And this is divided by now the derivative of the denominator, which is 4x cubed. Now, what's this limit? Well, here the limit of the numerator is 0 and the limit of the denominator is 0, so I can apply L'Hopital again to this situation. And when I do that, I should differentiate the numerator and denominator separately again. So the derivative of the numerator is, well, what's the derivative of minus sine x? That's minus cosine x. I don't need to worry about that minus 0. What's the derivative of plus x? Well, that's plus 1. And I'm going to divide by the derivative of 4x cubed, which is 12x squared. Now, what's this limit? Well, again, this is a situation where the limit of the numerator and the limit of the denominator are both 0, so I can apply L'Hopital again to evaluate this limit. So the limit of this is going to be the limit as x approaches 0 of the derivative of the numerator. What's the derivative of minus cosine? Well, the derivative of cosine is minus sine, but there's a negative sign there, so that's sine x plus 1. The derivative of 1 is 0, divided by, what's the derivative of 12x squared? That's 24x. But again, this is a situation where the limit of the numerator and the limit of the denominator are 0, so L'Hopital tells me to look at the ratio of derivatives. What's the derivative of sine x? Well, that's cosine x. And what's the derivative of 24x? It's just 24. And at last, I'm in a situation where it's not something going to 0 divided by something going to 0. Here, the limit of the numerator is 1 as x approaches 0, and the limit of the denominator is just the limit of a constant, which is 24, so this is 1/24. And because this limit exists, it means that this limit exists, which means this limit exists, which means this limit exists, which means this original limit is also 1/24.